In the section on corrective measures, we shall look at data augmentation. In the CSRNet paper, the authors propose this data augmentation scheme where they simply crop 9 patches from each image at different locations with a quarter size of the original image. Now the first 4 patches contain 4 quarters of the image without overlapping, while the other 5 patches are randomly cropped from the input image. Then after that, they mirror the patches so that they could double the training set. So that said, supposing we have this image right here, we could obtain this first patch. You could see clearly that it contains this region right here. Then we could also obtain this other patch, which happens to be this region. Then another patch, which is this region around this. Then another, which is this. So this first 4, we ensure that they don't overlap, so they don't touch each other. Then for the rest 5, we just crop from any position in the image at random. So we have this. Notice that this now matches up with this, or rather this overlaps with this. This too also overlaps with this. We also have this now that overlaps with, it doesn't overlap with any. And then we have, no, it overlaps because we have this point here. We have, it overlaps with this and overlaps with this. Anyway, we could pick the rest 5 at random. So there we go. Now, once we have this, as you could see, we've put all these different segments of the image together. And this is how we double our data set. So for this image, we now have this new image which is created. Now this process is repeated same for the density map to generate a density map wherein these parts have been recreated, as you could see right here. Then for us to train our model such that we have this sizes being equal, we'll just simply resize this so we have this. Now also note that we could define our model such that it takes in an arbitrary size. So we could define our model such that it takes the size and then generates an output 8 times smaller than this image or this input image size. So this means instead of having this in X and in Y, we just have known and then known right here, knowing fully well that with the input we'll get is going to be divided by 8 because we're going to pass through this 2 max pooling layers in the VGG model right here. Recall we had actually 3, not 2. So let's do this. Let's have our get base model summary, so we could see our 3 max pooling layers. There we go. We have this one, this and this. So clearly, no matter the input shape we have here, we would always have an output which is 8 times smaller than the input. And this means that we could take an inputs with arbitrary sizes, like say 500, because in the case where we actually recreate a data set, we're gonna have a new image which leaves from 768 1024, that's height width, to 576 768. So this means that we could take an input of the shape and we could also take an input of the shape, since this doesn't need the output to be fixed. Now let's run this, and there we go. We see that everywhere is known, so we could pass in arbitrary values right here. Now with that said, let's go ahead to implement the data augmentation scheme described in the paper. First, here we have this get rand, which permits us pass in a minimum value, maximum value, and then generate a random number in this range. So we could take, for example, get rand of say 0 to 30. It gives us 19. Then we have this in H in W, which is the same as in Y, equals this. Okay, so there we go. We'll run this. Now we have the code for getting the different patches which we saw on the slides. recall that this first four patches right here, this first four patches at fixed positions, because we want to be sure that they don't overlap. So that's it. And then we have now the last 5 patches right here, last 5 random patches from the image. So we have this first 4, last 5, the first 4, last 5. We're going to see why we're using this shortly. So firstly, we have our first patch. We'll decide to take the h mean coordinate as this height divided by 8, and then the w mean coordinate as the width divided by 8. Now note that if we have an image, we will have this, the height dimension, and then the width dimension. So we could decide to have this is the height, and then there's the width. So this is our origin. Obviously we have this origin, then we go up to the height divided by 8. So let's say we have this position. For the width dimension, we have the width divided by 8. Suppose we have this position, so we see ourselves around this position right here. Now what we do is we shift a certain number of steps to the right, and then shift a certain number of steps to the left, and there we go, we have our patch. Now the way we get this number of steps to the right and to the left is by simply using the fact that on the paper it was stated that each of these patches have to be a quarter of the image. So we shift by a quarter of the height to the downward, and by a quarter of the width to the right, and then that's how we obtain the patch simply. So normally this should be a bit bigger, so we should have this, and that's it. That's why we have this right here. And then this is when we take divided by 2, while the width is divided by 8, here divided by 8, the width divided by 2, here divided by 2, the width divided by 2. All this to ensure that they actually never meet. Now initially this height max and width max are considered to be zeros. Then later on we do the addition, which we just spoke of, where we have this patch 1 0, the patch 1 is this. So we're taking this coordinate, which is this, plus a quarter of the height. Then to complete the computation for the patch 1, we have the W max, which is the patch 1, that's the W mean, which is what we calculated right here. And it's this width divided by 8. Now plus the width divided by 4. And this is repeated for all these 4 patches right here. Now the difference with those 5 other patches is that they are gotten at random, so we use the getRand function, which we've defined already, to obtain this mean values right here. But then we ensure that this doesn't cross a certain limit, because if we pick the values for this h mean, w mean to be around the borders, then it may happen that when computing the h max, w max, we may have to go out of the image. So to avoid this, we make sure that this random values generated range from 0 to 3/4 of the height and 3/4 of the width. So that's why we do to make this choice right here. And similar to what we had seen already, initially this max values are at zeros, and then we simply go ahead to add up the height divided by 4 and then the width divided by 4 to obtain the h max and the w max. Once this is done, we have this patches, which takes in now each and every patch right here, patch 1, patch 2, up to patch 9. Then we shuffle this again, so that when recreating our image, we are going to have something that isn't resembling previous augmentations for the same image. Now the reason why we're doing the shuffling is mainly because of this 4 patches right here, because this already is gotten randomly. So for this 4 which are fixed, we just do the shuffling to change the positions. Now once we have this patches. Now note that also what's interesting is that from this we could obtain the corresponding patches for the density maps by simply dividing the patches by 8, since all the positions actually match up, given that we divide the image, which is the input, by 8 to obtain the density map. Now we could run this, and there we go. Here are our patches. We have the values for the H mean, W mean, H max, W max, and so on and so forth. Now if we take this off, we see that we always have the same values. The first 4 values are always the same. Let's take this now. There we go. We now have the coordinates for all the different patches. After getting all the different patches, we can now read our image. It's basically what we're used to doing already, which we're simply reading this image. And then for the image patch, this list we're creating right here, we are going to store the actual image patches based on those coordinates into this image patch right here. So that's why we have image patch.append. We take now the image array, which is basically the image, and then based on those dimensions of the patch or those coordinates of the patches. So if we take this patch, for example, let's take this one because it's the image. If we take this patch, for example, what we'll do is we'll simply take the H mean, W mean, H max, and W max. Or rather, H mean, H max. This isn't W anymore. This is H mean, H max, W mean, W max. So we pick out this I for this range of all the different patch coordinates. So here we have the patch coordinates, and then here we actually get these patches. So this means, for example, that in this case we could have something like 0 to say 272. Let's take this 0 to 192, and then this could be from 0 to 256. So there we go. Basically that's what we're doing. We're just picking out a portion of this image array. Take that back and we're fine. Now that we have this image patch, you see we just convert this to a tensor, and then we redo the same process but for the map patch now. So we create a map patch where, based on what we got from this density Gaussian map, we actually pick out this patch from it. Once that's done, we now have this final step where we define this new image. So this is this new image now, which will contain all the different patches which we've gathered throughout this 9 different points here. So we're gonna have this. We define this in new. You see, it takes the shapes. We could do this calculation to obtain the shape in the case where we have an input of 768 by 1024 by 3. Now this is going to give us the shape simply because if we have 192 by 256 and that we have to repeat this 9 times, it simply means we are doing this height dimension. Let's take this off. We're doing this height dimension 3 times, so it's just like doing this 3 times. We're repeating this also 3 times. So if you multiply this by 3, multiply this by 3, you'll obtain this, which happens to be 3/4 of the initial input. Now once we have this, we go ahead and create this new image, which we call imnew. Now that said, suppose we have this imnew gotten from which is going to collect all those different patches. It means we have this 9 different positions. So there we go. We have this, we have that, and then we have this right here. Now, so we have each patch 1, 2, 3, 4, 5, 6, 7, 8, 9 different patches to fit in based on the patches we've seen previously. And to fit this now, all we do is we just simply pick, for example, we'll go from 0 to 192 in the height, and then in the width we go from, when I is 0, we'll go from 0 to, like in this case, we'll go from 0 to 256. So that's how we obtain this. So this patch, we select this patch and we put in the value of the image patch which we had seen previously. Recall that those image patches, now there are 9 different image patches which we want to fit into this different boxes right here. Now when I is 0, we have the image patch 0, so we have the 0th image patch which will be fitted in here. So that's it. Now we are still at I equals 0. We move to this. We now shift the height. Basically what we're doing is we're shifting the height. So we now move to 192. So we're going from 192 to 192 times 2 basically. So we have 384. So this is the next. And then since I is 0, we still maintain this. So basically we're still going from 0 to 256. So now this is what we occupy. And then when we move to this, I is still 0, we have 2 times this. So we have 384 to 576. And then we have this portion right here. Now when I equals 1, you will see that we'll still go from 0 to 192 for the height. So the height from this to this, but then the width now goes from 256. So instead of starting from initial year, now we'll go from 256 to 256 plus 256. So that's it, 512. Now doing this and matching up with this, we see that we fall in this box right here. So we basically repeat this. We have this. When I equals 2, now we move to this, and this. So that's how we fill out all these different boxes, and the same is repeated for the mapping. Now that's understood, we could run this, and there we go. We see that we now have this image. Let's run this again so you could see how it's modified. Notice that it's going to change. So you see, there we go. So you see that we have actually done what's expected as of getting this different patches and then forming this new image which will multiply our data set size by 2. Then the last step now is just for this image, or rather this mappings. That's this Gaussian mapping we've seen previously. So our density maps, we should just verify to ensure that it's the same as the input. You see this head right here. Let's start from this. So we have a head. So you notice that we have this right here. If we go down, we see this head. It matches up with this head here, matches up with this other one here. This, you see this other head right here, matches up with this. You see this one, this. So that's it. Now at the center, you notice that at the center there's no head, so that's why you see the center looks empty right here. And then maybe this considered to be a head because it's very close to a head. It is not very clear from here. Now looking at this top, you see there are many people. Looking at this, you see because there are many people here, we have this different points. Then we have this point here. Let's look for a different image. Let's take this one, run that. Okay, now this image is better because there's some portions where there's no head. So this one, for example, is very empty. This empty. See, now this portions where you have this heads, you see you have this right here. See where there's so many heads, see this and that. So that's it. That's how we multiply our data set by 2. Now let's integrate this into our data generator. Now before integrating our data generator, let's note that we also define this new function generate new, which takes in a patch. Now note that this patch could be image patch or density map patch. It takes in this height dimension, width dimension. Note that the density map and the image would have different dimensions, so that's why we're taking this. And also even the images could have different dimensions. In the long run, we could have that data set with different heights and widths compared to what we have now. Now if it's an image, it's true. If it's not, we have this right here. And the reason why we're doing this is obvious. When it's an image, we have this channel dimension, and when it's a map, we have no channel dimension. So that's it. Now we repeat the same steps by just making sure that what we have now here are those variables which will vary depending on the input image right here. Now that that's been understood, let's look at this integration in our data generator. So here we have the X and Y. So X took this, Y took that. That was fine. Now we define this. We get our patches using the get patches function, which we've defined already. Once we get our patches, we go through the same process where we have the image patch and the map patches, which we actually obtain. And then the next step is to apply the generate new, and then get this image, this new image generated. We resize it to get the original size of the original size of the image. Now we had to find this to be in X and in Y. So basically we have here in H. So here we have in H, in W. Here we have in H divided by 8, and here in W divided by 8. So that's fine. Once this is done, we stack the two elements of our list, both for the inputs and for the outputs. So we could run this now. That's fine. Our base model has been run already, so we could go on with that. And also there's this point we didn't mention, is that we took off the reshape now in favor of this, because with the reshape we're obliged to specify its outputs, whereas now with this we don't have to specify the outputs, given that what we're just doing is we're taking off this last dimension, and to take that off it just suffices to do this, that is consider all previous dimensions, and then for the last dimension take just the 0th value. And if this is okay, we can now train. See, let's take this back. We'll train. We're getting this error. That should be because when this generator, we made this error of doing this resize based on the modified version of the height. Note that we have modified the height to match up with a new image generated, so this height had changed and it's no more the initial height. So that's why we should take X and then Y. X, Y. So that's it. Run this again. And it works just fine. We've gone out of memory. We just have to restart. Now note that depending on your computing power, restarting may not help. So in that case, you may have to reduce these dimensions right here. So you have to resize our inputs such that we have smaller inputs which could get into the GPU's memory. Nonetheless, with this GPU, when we restart and clear our memory, we could actually train on the inputs and the augmented inputs. So let's run this. Everything is going to work fine now. Run our data generator, run that, different models, go ahead and train. Now we see that it trains. We've cleared our memory, and there was now enough space for it to train on this data set, which has been augmented. After training for around 30 epochs, you have the results we obtained. Let's now pause the training and then see what the kind of maps it generates. So test with this training set data right here. The density map generated is not bad, although the number of people predicted is not exactly the same as this, but the model is learning to generate this density maps correctly. Now let's test on others, say 245, which is what we had on the slides. See, we have 74 right here. And obviously this will get better as we continue with training. Now let's test on an image which is not in our data set. We'll test with this image, which we call people 3. There's several test images which we used. Basically we'll run this, and then we observe the density map which is generated from the input image. You see how it looks close to the input image we have. And also note that this image doesn't look like a typical image from our training data set. So our model is learning quite well and generalizing even when the test set isn't looking as the training set. Now also note that in practice you will have to, depending on the kind of problem you want to solve, get as much data as possible. So if you're having a camera, CCTV, which is placed in this kind of position, it's better for you to train on more of this kind of data. Whereas if your CCTV is placed such that this images look more like this, then it's better to train on this kind of data. So it's very important to take note that the model isn't of great use if you don't pick out the right data to train that model with. So that's it. Let's now count the number of people we have in this image. Now after segmenting this image into these different parts, we count this number of people: 7 plus 29 plus 26 plus 20 plus 18, 14, 14, 14, 17, 28. This gives us a total of 187 people, and we see that our model did quite well because it predicted 180 people, so we missed out on 7 people. And this is also normal because we have this polls right here, which for this person, for example, see, it wasn't very clear and stuff like that. So it's also important to note that in a case where you are going to be predicting people where there are polls like this, it's important to have as much data as possible where you have this kind of polls, so that our model learns to differentiate between the polls and maybe the people's heads. Like this poll seems to block this person's head, like right here. So it's very important to take note of the data set you're working with. So it's very important to work with data set which is representative of the kind of data your model will be receiving once it has been deployed.